Yeah, we're done with lectures.
So 2 more lectures and we're done with lectures. It's
What do
just a
we-
bunch of testing.
Alright.
Well, it's only one test, right?
No, 2 tests.
Yes.
2 tests at least. Maybe I'll throw a third one in there.
A third one for what?
For fun, yeah. Anyways, yeah, starting chapter 7 today, starting transcendental functions. Basically, functions that can't be represented with your basic algebraic expressions of times, exponents, those types of things, like polynomials. Anyways, the first one that we're going to be talking about now is inverse functions. So 7.1 is all about inverse functions. I don't know, have you encountered inverse functions before?
On my calculator, but nothing else.
Calculator only, but that's about it.
Yeah.
All right, it's a pretty straightforward definition. An inverse function, it just swaps your x's and y's on your functions. Your inputs become outputs and your outputs become inputs. The inverse function is a function that undoes your initial function in some sense. So remind us of what a function is. What is a function? A function is just a set of ordered pairs where every left-hand element is paired with a unique right-hand element. You know that when you have a function, if your inputs are the same, then your outputs must have been the same.
Yeah.
And we had what we call the vertical line test. So an example of something that's not a function is right here, x squared plus y squared equals 9. What is that?
A circle.
That's a circle centered at the origin with radius 3. Perfect. And so that roughly looks like, extremely roughly, that thing. And notice that for a particular input here, what's the output?
You have 2.
You have one up here that has a height there and it has a height there. So one input gives us 2 outputs. That is bad. This does not pass what we call the vertical line test. If something's a function, every vertical line you draw through it should only intersect the function at a single point. If it doesn't, then it's not a function. So, a couple ways we think about functions. Every input has a unique output, or you can think about in terms of the vertical line test. Make sense so far? Okay. Now, we have a notion of a function being 1-to-1. Now remember, it's a function if every input has a unique output. The function's 1-to-1 if every output comes from a unique input. So a function f is 1-to-1 provided that if the outputs are equal, then your inputs must have been equal. In this case, it has to pass what we call the horizontal line test.
Oh, really?
So giving an example of a function that is not 1-to-1, we'll look at this function. Y is equal to x squared plus 1. What is that? It's just a parabola shifted up 1 unit. So it starts out right here. If you plug in 1 to that thing, you get 2. If you plug in -1, you get 2. If you plug in 3 to that thing, what do we get? Or sorry, if you plug in 2 to that thing, what do you get?
5.
5. So 2, 3, 4, 5, somewhere like right here. And if I plug in -2 to that, what do I get?
5.
5. So notice that if I told you, I say, look, my output was 5. What was my input?
2 or -2.
It was 2 or it was -2. There's no way for you to know. Right?
Yeah.
And so, notice that if the outputs are the same, that does not imply the inputs are the same. What was, in this case, using this as our function, what was f of 2 equal to?
5.
5. And what was f of -2 equal to?
5.
Same.
5. So notice that we had f of 2 was equal to f of -2. However, 2 is not equal to -2. Your function is 1-to-1, trying to wrap your head around this definition. If the outputs being the same implies the inputs were the same.
Yep.
Here's a counterexample. The outputs are the same, but the inputs are very different. So it's not 1-to-1. And if we try to very roughly sketch that thing in there. Okay, there it is very roughly. It does not pass the horizontal line test. Think about if a horizontal line intersects it at 2 points, then that means that for this height, there were 2 points that gave me that height. So my horizontal line at 5 intersects the function twice. That means that there's 2 points who have their output as 5. So it is not 1-to-1.
Okay.
Good?
Yeah.
Okay, so now let's look at something that is a function and is a 1-to-1 function. y is equal to 2x plus 1. This is both a function and it's 1 to 1. I tell you that my output was 9. What was my input?
4.
4.
Yeah.
Because 2 times 4 plus 1 gives you 9.
Yeah.
And if I gave you any output, you can figure out the input that went to it.
Yeah.
Writing it as a quick sketch of a proof, proving that this is 1 to 1 using this definition, let me just quickly scratch out that proof. Let's assume that I told you, we'll scribble it over here. Let's say that I told you f of a was equal to f of b. What is f of a if this is our function?
It's 2a plus 1.
It's 2a plus 1. What is f of b?
2b plus 1.
2b plus 1. So if f of a equals f of b, then 2a plus 1 equals 2b plus 1. Subtract 1 from both sides. That gives me that 2a is equal to 2b. Divide both sides by 2. That gives me that a is equal to b. So if f of a equals f of b, then a equals b with this function. And so, quick proof that it is in fact 1 to 1 using that definition. Trying mostly to get you to wrap your head around how this definition gives us what we want.
Yeah. Okay.
Okay, so, and then drawing this thing out. What is it's a line that goes through the y-intercept, or the y-axis at 1 with the slope of 2. So it goes through right there, comes up right there, comes down right there, and then drawing it in very roughly. There she is.
Yep.
And notice that it passes both the vertical line test and the horizontal line test. Every vertical line intersects it one and only one time. Every horizontal line intersects it at most one time is all we care about. Good so far?
Yeah.
Okay. So now we're going to talk about an inverse function. It turns out that only one-to-one functions have inverse functions. Not every function has an inverse. Only one-to-one functions have an inverse.
Okay.
And we'll try to give you some intuition for why that's the case. But if f is 1 to 1 on some domain D and it has its range R, then f inverse, the way we represent an inverse function is the exponent -1 there. Now, do not fall for this trap. F inverse of x is not equal to 1 over f of x. This is not an exponent. It's just a different symbol. All right? We could have just as easily drawn a square right there to mean our inverse function. They choose to use that -1 exponent. That is not an exponent. We are not raising it to the -1 power. It's just a symbol for a function. It's just a symbol for the inverse function. That's all it is. Okay, so the inverse function is defined by the inverse of b is equal to a if and only if f of a equaled b. So if plugging a into f outputs b, then plugging b into f inverse of a has to output a. I think I said something weird, but I think you understood me right. If f of a equals b, then f inverse of b equals a. This takes inputs and gives us outputs. This then takes the outputs and maps them to their inputs. Now notice that if a function isn't 1 to 1, I can't map the outputs to the inputs.
Well, can't you just list them off?
No, because let's look at the output 5 on this on this parabola. What was its input?
2.
You don't know. It could have been 2 and it could have been -2. So since inverse functions map outputs to inputs, it only works if every output has a unique input. Or in other words, if the function was 1 to 1.
Does the function also have to be on 2?
No.
No?
Now, you can restrict the domain and the range as much as you would like. So we'll look at an example where we do just that.
But if the range is larger than the domain, how do you map everything back?
If the function already had to map, if it's 1 to 1, every input to one and only one output. There is going to be some restricted domain that you could find, and some restricted range that you could find, so that once you restrict it, then yes, it's also on 2.
Okay.
So there would always be a way of setting up the domain and the range so that the function is a bijection.
Okay.
So first, just using our intuition now, let's come up with the inverse function here. So f of x is going to be the function 2x plus 1. What is this? It's exactly what we have over here. It goes through 1, and then it goes over 1, up to, over 1, up to, whatever. Something that looks roughly like this thing. Very roughly. I don't know why my hand's squiggling so bad. Jeez. Very wavy line. Okay. Now let's just think about this for a second. What is its inverse function? So what does this function do? It takes an x, and what does it do to that x?
Times it by 2 and adds 1.
First it doubles it, and then it adds 1 to the result.
So
let's undo that. Let's undo what this is doing. This is a function, it takes something, it doubles it, then it adds 1. What's the reverse of that?
you have it minus 1.
First you minus 1, and then you half it. This first doubled, and then added 1. So if we're going to undo that, we've got to subtract 1, and then half it.
Okay.
So the inverse function would be, we take our x, first we minus 1 from it, and then we half it.
Okay.
Let's just play with this for a second. Really quick, what is f of 5?
2.
5 times 2 is 10. Plus, oh, you did that. F, not f inverse. F. F of 5 is 11. So now what is f inverse of 11? When I plug 11 into this, what do I get? 5. 11 minus 1 is 10, divided by 2 is 5.
Yeah.
And so you'll notice that if this maps 5 to 11, this maps 11 to 5. It in some sense undoes it. More generally, watch what happens. Let's look at f of f inverse of x. See what we get.
You're going to get 2x plus 1.
I'm going to plug this in to this function.
Oh, I see. You're going to get 2. Wait, what?
You're just gonna get
Let's see what
You're
happens.
going to get x.
So I'm going to plug this in to this function.
Okay.
So we're going to do, let me just write some notation here just to help us be clear. So f of, what's f inverse? X minus 1 over 2. Okay, that's what I'm plugging in. So plugging that into x, we're going to get 2 of what we're plugging in plus 1, right?
Yeah.
Just plugging in f inverse to f. And so, 2 and 2 in the denominator, those cancel out, leaving me with
ones.
x minus 1. Plus 1 gives me
X.
just x. So they undo each other.
That makes sense.
And in like manner, if I would have figured out f inverse of f of x, that would have been f inverse of 2x plus 1, which is equal to, if I plug in 2x plus 1 for x right there, 2x plus 1 minus 1 is just 2x divided by 2, just gives me x. So that's not an accident. This will always and forever be the case. F of f inverse of x will always be equal to just x, will also be the same thing as f inverse of f of x.
Yeah.
F takes x and maps it to something, and then f inverse undoes that mapping. F took 5 and mapped it to 11. When I plug 11 back in here, it maps it back to 5. And we're back to where we started, wherever we initially plugged in. They just undo each other. Now, you kind of just thought in your head how to come up with this inverse function. Let me show you how we just calculate inverse functions in general.
Yeah.
So we start out with this. Let me rewrite it in terms of y. You with me so far? Now, since an inverse function is just what happens when you swap your x's and y's, then this function, the way you get the inverse, is just swap the x's and y's and solve for x.
Okay.
And resolve for y. So swap your x's and y's, and what do you get? X is equal to 2y plus 1. This is going to be your inverse function. If this was your function, your inverse function is what you get when you swap your x's and y's. It's just swapping your inputs and outputs.
Yeah.
That's all the inverse function does. And now just solve for y, and you get your inverse function. So let's see, move the 1 to the other side, but I'm going to write my 2y first, so that's equal to x minus 1. I move that to the other side and swap the order I wrote them. Divide both sides by 2, you get y is equal to x minus 1 over 2. So if this was our function, this was our inverse function. If that's our function, there's our inverse function. So that's how you can always just calculate these things by hand. You don't need to just kind of cleverly think about it. Just swap your x's and y's and solve it. What's the inverse function? It's the one that swaps inputs and outputs. Let's see that pictorially now over here. Let's graph this in. X minus 1 over 2 is the same thing as, I'm just going to distribute the 1/2 through. 1/2 x minus 1/2. Same thing. You see how that's the same thing?
Yeah.
I'm just trying to get in the easiest form for you guys to graph it the way you know and love. Okay, so let's plot this function now. Where does it cross the y-axis? We got it, everyone.
Yep.
It crosses the y-axis down here at minus 1/2, right? And what's its slope?
1/2.
1/2. So if I go over 2, well, let's see, if I go over 1, I go up 1/2, just to get us a point. And if I go down 1/2, I go back 1. And now from here, if I go over 2, I only go up 1. From down here, if I go down 2, I have to go back, or if I go down 1, I have to go back 2. And hopefully I can draw this half decently. Okay, that's trying to draw the inverse function here. So, minus that, that's our red one. And now, notice what would happen. This point right here, what are the coordinates of this point?
1, 4.
1, 3, right?
3. Yeah.
That is a point 1, 3. What that means is 3, 1 has to be on this function. If 1, 3 is on here, swap it, 3, 1 has to be on here. 1, 2, 3, 1. What are the odds?
What? 100%?
He's saying.
Since the point 1, 3 is on this function,
Yeah.
then the point 3, 1 is on this function. Why is 1, 3 on this line? Because when I put 1 as an input, I get 3 as an output.
Yeah.
The inverse function does a reverse. If I plug 3 into my inverse function, it has to give 1 as the output.
Okay.
So if the point 1, 3 is on this function, the point 3, 1 has to be on this function.
Okay.
Over here is the point 0, 1. So over here has to be the point 1, 0. This line is just the exact same line you get here if you just swap all your coordinates around. Swap all your x's and y's. That's what we were doing in the math right here. Here's our function, swap the x's and y's. There's our inverse function. The exact same thing. If xy is on this function, swap yx is on this function. Go ahead.
What are the inverses of the trigonometric functions?
The inverse,
Like sine of x and stuff like that.
so that's something you do in trig. I don't know, have you gotten to the inverse trig functions? Arc, sine, arc, cosine, arc, tangent. They're the functions that take coordinates and spit out angles. Instead of taking angles and spitting out coordinates.
It looks the same. It will say sine and then have a negative line in the next one.
Yeah, so your arc sine function just looks like this. Sine inverse of x. And it spits out some angle, theta. So there are your inverse trig functions. What exactly those functions are and how you write them out is something that trig students don't know how to do. And so the way you think about it is just it's doing the inverse of what you do when you look at a unit circle. Instead, if you're looking for arc sine, so the arc sine of 1/2 would be, where's sine 1/2? Pi thirds. And so the arc sine of 1/2 would be pi thirds, because pi thirds is where your sine is 1/2.
Okay. That's cool. Alright.
Okay, anyways, so in general now, trying to draw some general picture here, sorry I didn't draw it too well. I've got some red function, and I've got its inverse function, the peak function. And if the coordinate x naught, y naught is on our red function here, so here is the coordinate x naught, y naught on our red function, then the coordinate y naught, x naught has to be on our inverse function.
Yeah.
And the way we think about it, the way you could quickly picture what an inverse function looks like, is it's what happens if you just reflect it across this line, y equals x. If you just reflect it like that, you get your inverse function.
Oh yeah.
That's what happens when you swap all your x's and y's around.
And that one was flipped?
That was trying to be drawn as flipped.
Well, I'm saying the one above that.
Yes, so take this, and kind of reflect it right there. It's like what you would see if you stuck a mirror perfectly on that 45 diagonal.
Yeah.
Yeah, okay.
Make sense?
Yeah, makes sense.
So, pictorially, that's what's going on. Try to give you all the intuition I can about this. So, let's do some more examples. We're just going to find the inverse functions.
Okay.
So here I have f of x is equal to 1/2 x plus 1.
Yeah.
What do I do first? First, I'm just going to write that.
We're finding the inverse?
Yeah, we're looking for f inverse of x now.
Okay,
You're
we
gonna
do switch the y
Yeah,
to x.
switch the
Well, first rewrite it with a y. So y is equal to 1/2
x plus 1.
x plus 1. So there's our function.
That you put 1 right that way.
Thank you. Okay. So there's our function. Now just swap your x's and y's and you have your inverse function.
Yep.
So then our inverse function is x is equal to 1/2 y plus 1. We got to solve for that y.
So -1 times 2.
Add 1 to, or subtract 1 from both sides. So I'm going to get 1/2 y is equal to x minus 1. Just subtracting 1 from both sides, right?
Times 2.
And then multiply both sides by
It's
2.
-2.
And I get y is equal to 2x minus 2. And there's our inverse function. Or to finally write our answer out, f inverse of x is equal to 2x minus 2. This is the inverse of that.
And there's no quicker way just to look at that and just solve it?
You could have kind of thought about it if you wanted.
Yeah, kind of right there.
We're looking for the function that subtracts 1 and then multiplies the result by 2. So x minus 1, then multiply everything by 2.
Yeah.
2x minus 2. So yeah, you could just think it through if you wanted. Okay, now let's look at this one. F is equal to x squared. Uh-oh, x squared is not a one-to-one function.
Yeah.
Oh, well, your domain is restricted.
But we restricted the domain. We said on 0 to infinity.
Yeah.
So now what does that function look like? It looks like, here, let me just change it from the author's example, just like we already have drawn, x squared plus 1. And we'll look at this on the domain 0 to infinity. So now what we're looking at is red here, starting there and just keeping the right-hand side.
Yeah.
So our domain just goes from here to here. So what is our domain on this function?
It's that.
Our domain is equal to 0 to infinity. What is our range equal to?
It's going to be 1 to infinity.
Our range is equal to 1 to infinity. So now when we find this thing's inverse function, whatever it is, its domain is going to be from 1 to infinity, and its range is going to be from 0 to infinity.
Okay.
And now let's find its inverse function. So finding the inverse function of this. First, just write it as y equals
X squared minus
x squared plus 1. Okay. Now what do we do?
You're going to swap them. So it's going to be x.
Swap them.
X is equal to y squared plus 1.
So I got x is equal to y squared plus 1. Now what?
Move the 1
Move the 1 to the other side.
and then root.
So I'm going to write y squared is equal to x minus 1. Well, I'm going to write y is equal to plus or minus the square root
Of x minus 1.
of x minus 1. Now, let's think carefully. Do I ever have my negative case here?
No.
No.
No. How do I know that?
So you're restricted your range.
Because my domain was from 0 to infinity.
Yep.
Okay.
Right?
Yeah.
So,
Yeah. Okay.
piggybacking on this picture, red, we'll kind of get red purple here. And I'll draw its inverse now in purple. So red is the function we currently have. It starts here at 1 and it goes like this, right?
Yeah.
It's that half of the parabola. Its inverse function, let's plot this thing. Well, that's just a square root function. We just have the positive one. That's just a square root function shifted 1 unit to the right. So that starts out, try and do it in purple. That starts out right here. And then when you plug in 1, you get,
0.
or sorry, when you plug in 2, you get
1.
1. And when you plug in, let's see, 5. 1, 2, 3, 4, 5. Then you're up here at 2. And so we get our square root function
Shift it over right one.
like this. And so notice, what's the domain of purple?
Positive.
1 to infinity are what we could plug in. And this will go up forever, and the range, so is going to be 0 to infinity. square root, it goes slow, but it grows forever.
Yeah.
Right? So you see how that's just kind of the reflection of that? Minus my bad drawing. Okay. So, our inverse function, if we were to finally write the inverse function, f inverse of x is equal to the square root of x minus 1. Okay. Now, just so we don't get confused, that is all not part of this now. Okay, so now we're going to prove how we take the derivative of inverse functions. Because this isn't just about working with inverse functions. You were supposed to learn how to do that in your algebra courses. Now, we're going to learn how to take the derivative of an inverse function.
Okay.
So I'm going to prove that the derivative with respect to x of some function at the point y naught, some point that we give it, is equal to 1 over the derivative of f, not of f prime, of f at the point x naught. The point x naught that mapped to y naught.
Is that f? That's f, right?
Yeah, that's f prime. That's a prime right there.
Oh, f prime is your derivative?
Yes. In other words, what this is saying is the slope of your inverse function at y naught is a reciprocal of your slope at x naught. Let's take our picture over here. Give me a value x we want to use. One that we're going to plug into here. So give me some value x.
3.
3, we're going off our picture. We'll use 2. 2 or 1. Can we do 2? I think we can do 2. Let's do 2. So at 2, if I call x naught 2 here, so I'm calling my x naught here, here's x naught, which is 2. You with me? What is my y naught?
1.
My y naught now is up here at 5. It's what x naught maps to.
The red line and the purple.
Sorry, forget this thing. Our function, let's just write it over here. We keep piggybacking on this. Our function f of x is equal to x squared plus 1.
Okay.
And our inverse function is the function square root of x minus 1.
Yeah. Okay.
Okay. So, just looking at this function, what is the slope right here at x naught? What is the slope at x naught? Sorry. No, that's the height. So x naught is 2.
Tells me. Oh,
X naught here is a concrete value 2.
yeah.
And y naught is a concrete value 5.
So the slope's 4?
So the slope is 4. Just take the derivative of that. You get 2x. And plug in 2 gives you the slope.
Oh.
So over here at x naught, if we were to measure the slope of that thing, it would have a slope of 4, which makes sense. That's a very steep rise right there. What does this mean then? It means that over here at y naught, if we go over to 5, so 2, 3, 4, 5, here's y naught. And we look at the slope of, is that 5? 1, 2, 3, 4, 5. I plotted that wrong. That point was supposed to be right there. That still kind of goes the same way. Whatever. Shouldn't be yours. Okay. That means over here at y naught, this function slope is
1 over 5, 1/5.
1/4. This one was 4, so this one is 1/4.
Yeah.
So the slope of this function at x naught is a reciprocal of the slope of this function at y naught.
Okay, that makes sense.
Yeah.
So there's trying to see it pictorially. We're going to prove that that is actually the case. I'm just trying to get you to be able to read what this is saying.
Okay.
Now, what is x naught? It's the point that was mapped with y naught. So another way that you could write this is the derivative of f inverse at the point y naught is 1 over the derivative of f at x naught. What is x naught? It's f inverse of y naught. Because y naught is equal to f at x naught, right?
Yeah.
So x naught is equal to f inverse at y naught.
Yeah.
You with me?
Yeah.
So this and this are saying the same thing. The derivative at x naught, which is the same thing as the derivative of f inverse at y naught. The point paired with x naught, or the point x naught mapped to in your function. Here's the actual equation that the author gives in the book. So the derivative of f inverse at the point B is 1 over the derivative of f, where you plug in f inverse of b. It's just this exact same thing, but he's using b's instead of y's naughts. And that's what you'll see in your book as a formula.
Okay.
B.
This b one. Here's the way I always think about it, but that's just my own thinking.
I like that.
Okay, so with that, let's actually prove this thing. Okay?
Good.
So, I'm looking for the derivative with respect to x of f inverse. If I'm going to think about this as a function in terms of y, then I'm going to call it the derivative with respect to y.
Okay.
As though it's taking outputs rather than inputs.
Okay.
Just because I'm going to use my x's for what I plug into f. And so I'm going to use y's for what I plug into f inverse.
Okay.
Notation is identical though. Okay, so the derivative with respect to y of f inverse at the point y naught. Now by definition, what is that? Definition of a derivative. That is the limit as y approaches y naught of kind of a, let me just write this one smaller a little bit. F prime of x naught. Okay, so then this is a limit as y naught approaches 0 of f inverse at y minus f inverse at y naught. I just wrote that way too tall. Let me go down more. So I'm not hugging that. Okay, do it again. The derivative with respect to y of f inverse at y, or at the point y naught. Okay, by definition, this is equal to the limit as y approaches y naught of, and it's just our difference quotient,
Yeah.
f inverse of y
Minus.
minus f inverse of y naught
Over.
all over y minus y naught.
Yeah.
You with me? Now, let's think about this for a second. If y is equal to f of x, then f inverse of y is equal to x.
Yeah.
They just undo each other. If f takes x and maps it to y, then f inverse takes y and maps it to x. If f took 5 and mapped it to 11, then f inverse takes 11 and maps it to 5.
Okay. Yeah.
Good?
Yep, that makes sense.
So, notice that these two things are going to be true. What is y naught? It's what x naught mapped to. What is y? It's what x mapped to. So I may be making those substitutions right here.
Okay.
So, what is f inverse of y? X. What is f inverse of y naught?
X naught.
X naught. What is y in terms of x?
X. In terms of what?
What is y in terms of x? It's just f of x.
Oh,
Yeah. That makes sense.
And what is y naught in terms of x naught?
F of x naught.
F of x naught.
Just their reciprocal of.
So we haven't taken our limit yet, but so far we've got this thing, right? The limit of that, which is the same thing as the limit of that. Now, what is a property f has to have in order for us to have an inverse function?
It's 1 to 1.
It has to be 1 to 1. So, as y gets closer and closer to y naught, it also has to be the case that x gets closer and closer to x naught.
yeah.
Let me explain to you why that isn't the case if your function isn't 1 to 1. So let's say for a sec, we've got a parabola. Here's x naught. Here's y naught. You with me? Now, if I know that my function's height is getting closer and closer to y naught, it could be doing it over here. That does not necessarily mean that my inputs are getting closer and closer to x naught.
Yeah.
They're getting closer and closer to some value over here.
Okay.
But if my function is 1 to 1, so say instead we have a cubic, now I know if my function's height is getting closer and closer to y naught, then my inputs must be getting closer and closer to x naught. So in the special case, whether your function is 1 to 1, then the limit as x approaches x naught is the same thing as the limit as y approaches y naught. That is the case when your function is 1 to 1.
Yeah.
Makes sense.
So this now is the exact same thing as the limit as x approaches x naught of, and now I'm just going to, tell me if I lose in the algebra here.
Okay.
1 over f of x minus f of x naught all over x minus x naught. Maybe seeing how this is the same as this is easier. What's 1 divided by something? It's just its reciprocal.
Okay.
So if I want to divide it by 1, flip the reciprocal. If I want to put it back up, flip the reciprocal. Another way to just kind of see it is 3 over 1 is the same thing as 1 over 1/3.
Yeah.
How many times can I divide 1 into thirds? 3 times.
Okay, yeah. Okay.
Okay. So same thing here. So this limit is now equal to this limit. But what is this limit now? The limit of a quotient is a quotient of the limits. So what is the limit as x approaches x naught of 1?
1.
1. What is the limit as x approaches x naught of f of x minus f of x naught over x minus x naught?
1.
No? That's a definition of the derivative.
Yeah.
That is a derivative of f at x naught. Concrete, the derivative. Going back to basic definition. The derivative with respect to f at the point x naught is equal to the limit as x approaches x naught of the difference quotient. That's the exact definition of a derivative.
Yeah.
That's exactly what we have right here.
Okay.
So the limit as x approaches x naught of this is just the derivative of f at x naught. That's all it is.
Makes sense.
Yeah. Okay.
Good?
Okay. Yeah.
Okay.
There we go.
So we took our limit and there it is, which is what we were trying to prove. Now what is x naught? If we want to get this back in terms of y naught, what is x naught?
It's f.
It's whatever,
Inverse.
it's f inverse of y naught.
Yeah.
Yeah, so this is also the exact same thing as 1 over f prime of f inverse of y naught. Same thing.
Makes sense.
Okay. So, there it is. Da-da-da, square box. We're done. There's a quick proof.
Okay.
All right. So now, let's do some quick examples. Just to get comfortable using this formula and see how it works. So first off, we're going to look at the function, just f of x equals x squared, with its domain restricted. So just the right-hand half of that, from 0 to infinity.
0 to. Okay.
Yeah. Okay, so its inverse function is just going to be the square root function. You with me?
Okay.
Now let's find the derivative of f prime of x.
Okay.
Or not f prime of x, f inverse of x. Let's find the derivative of this thing, which is just the derivative of the square root. So what is the derivative
X to the 1/2. Or
with respect to x of
yeah,
f inverse of x?
X to the 1/2.
That is.
So yeah, we're doing the same thing as a derivative with respect to x of x to the 1/2. Okay, you guys are in trouble if you can't do this in your sleep.
It's X to 3 over 2, and then pull it down to 3 over 2.
No, you're doing the integral. We want the derivative.
It's
Bring
1
down
half
the
x.
exponent, subtract 1.
Yeah, it's 1/2 x to the power of -1/2.
So it's 1/2 x to the minus 1/2.
Yeah.
right?
Yeah.
Yeah, that's right.
Now minus 1/2 is the same thing as 1/2 in the denominator,
Which is, yeah, flip it.
which is just a square root. So this is just 1 over 2 square roots of x.
Yeah.
You follow
Yeah.
that?
Yeah.
You guys, you better know how to do this.
We do.
Okay, you do. You can do it in your sleep, so you're trying to go to sleep to do it. Okay. So now let's use the formula to calculate it.
Okay.
And this is just to see that it gives us the same thing.
Yeah.
In this case, this is not the case where you would want to use this formula. But just to show you, it gives you the same thing. So now, once again, let's find the derivative with respect to x of f inverse of x. What is this equal to? It's equal to 1 over f
Derivative.
prime of f inverse of whatever that thing was.
Okay.
Whatever you put there is what shows up there.
So x.
So it's 1 over
So it's 1 over, just blindly using our formula for a
the
second,
square root of
f prime of f inverse of x.
Okay.
Just blindly using our formula, not even thinking.
Yeah.
Okay. Again, this is just 1 over f prime of, what is f inverse of x?
Square root of x.
It's just the square root of x.
Okay.
Okay, and then what is f prime?
2.
F is x squared, so what is f prime of x?
It's 2x.
It's just 2x. So now plug the square root of x into 2x, and you
Just
get
x.
1 over 2 square root of x,
Yeah.
which is the exact same thing as what we got before.
Yeah.
Interesting.
So there's using the formula.
When is the formula useful? Does it
We'll
work?
see an example here where the formula now is useful. So this time I want to find f inverse's derivative at 6.
What?
I want to know, so that's f inverse prime at 6. I want to find the derivative of f inverse at 6. What is the slope of f inverse at 6?
Yeah.
That's what I want to know.
Okay.
You with me? Where f is a function x squared minus 2.
Okay.
Now really quick, what can I plug in here to give me 6? 2.
Two.
You guys are quick.
I thought too, I just didn't want to say it.
Alright, so 2 is what maps to 6.
Yeah.
So if this is our y naught, this is our x naught. This is a thing paired with 6. You with me? Okay. And now, finding the inverse of this thing is one way that we could do it.
Well, could we just switch
But
over?
what's easier, finding the inverse of this thing or finding the derivative of this
The
thing?
derivative.
The derivative is easier to find than the inverse.
Okay.
So we're going to be able to calculate this without ever figuring out what our inverse is.
Oh, wow. That's
Well-
So f prime of x, in this case, is just equal to 3x squared, right?
yeah.
So then, I know that f inverse prime at 6 is equal to 1 over f prime at,
Where are we?
we're using this formula,
So what's f?
or we're using this formula, whatever you want.
So what's f inverse?
We don't know what f inverse is. But what is f inverse of y naught?
X naught.
X naught. What's our x naught in this special case?
Six.
Oh, it's 2.
What's the thing that mapped to 6?
2. It's 2.
2.
Okay.
That's pretty cool.
Here's probably where you want to best look at it. What is the derivative of this thing? It's 1 over f prime of x naught. What's the slope of this at y naught? It's 1 over the slope of f at x naught. There's our y naught. Our x naught was 2, the thing that paired to y naught.
Okay.
And now plug 2 into this, and what do you get? 12, so it's just 1/12.
Gotcha. Okay.
And that might have seemed like there was a lot of talking going on, but once you understand it, see how quickly you could have figured out this thing. I look at this, I say, what maps to 6? 2 does. Calculate this derivative in my head, 3x squared, plug in 2, 12, 1/12. Like, it wouldn't have been that impressive for me to just tell you what the answer was just looking at it, not having to do any algebra. That would have been some impressive accomplishment once you get what's going on.
Okay.
And that's the point, is it makes it go much quicker. So it's possible for you to find the slope of this function at a point without even knowing what the inverse function is. And that's where it becomes super useful.
That makes sense.
Because imagine, for example, that you were working with trig functions now. Who likes working with inverse trig functions? Nobody.
Pretty easy.
You'd rather just work with the trig function directly. And trig functions we know how to easily calculate derivatives of. Gotta move your backpack so I can slide this. Alright. Any more questions on this before we switch gears?
That's pretty
Is the other
straightforward.
one the same concept or
No.
completely different?
Alright.
Can I grab some water?
Yeah. So this next section, I almost debated skipping 7.2 and going to 7.3 and then coming back and doing 7.2. 7.2 is on logarithms. 7.3 is on exponentials. And for some reason, this author wants to do exponentials after logarithms.
Really?
Yes, it makes 0 sense. I don't particularly like how he does it. So I'm kind of going to I am going to stray so far from the book in how I cover this next section.
Okay.
I'll cover everything the book covers, but we're going to be way smarter than this author. It's baffling what he does.
Thomas.
Huh?
Thomas.
Yeah. Now, I'm going to assume that you guys aren't very comfortable with logarithms if you've ever even seen them before. Is that a fair assumption?
Yes, that is correct.
Tends to be the case for,
Overboard.
what?
I said a little overboard.
Little overboard. So, let's cover what logarithms are.
Okay, let's do this.
Before we do that, we need to cover really quick exponentials. Because a logarithm is the inverse of an exponential. In the strict sense, like what we were talking about over there.
An exponential is
A logarithm undoes an exponential. A logarithm is the inverse of an exponential.
Yeah.
exponent.
Exponential.
An exponential.
An exponential function, f of x, is something like 2 to the x.
Oh, that's right.
Not x squared, 2 to the x.
Yeah.
Okay.
That is an example of an exponential function.
We haven't done
A
one.
function where the variable is in the exponent.
Interesting.
Anyways, so let's get comfortable with some properties of exponents.
Okay.
Some that hopefully you know these ones. What is anything to the power of 0?
1.
1. A to 0, 1. What's a to the power of 1?
A.
Itself.
A. Look at you guys. What is a to the m times a to the n?
A to the n plus n.
A to the n plus n.
A to the m plus n. When you multiply terms, you add exponents.
Yeah.
What is a to the negative 1?
1 over a.
1 over a, or 1 over a to the 1, however you want to think about it.
Yeah.
What is a to the m to the n?
A to the n times n.
A to the m times n. An exponent raised to an exponent means you multiply the exponents together.
Yeah.
And then finally, give a little bit more space here. A to the m over a to the n is equal to what?
A to the n minus n.
A to the m minus n. If we want to bring that upstairs, it makes it negative, and then when you multiply terms, you add the exponents. So adding a negative n.
Okay.
Okay, now, definition that the author avoids altogether of a logarithm. When we say that y is equal to the logarithm base a of x, that is the same thing as x is equal to a to the y. This is very hard for you to get comfortable with initially. But if our exponential spits out an x, then our logarithm takes the x and spits out the y. An exponential takes some base and multiplies it by itself a bunch of times to spit out x. Right? So I'm going to refer to this as a product. So with an exponential, you give it the exponent and it spits out the product. With a logarithm, you give it the product and it spits out the exponent.
So it's the inverse of the exponential.
Yes, these are inverses of each other. If y is equal to this, then x is equal to that.
Okay.
Good so far?
Yeah.
Now this is best understood with a bunch of examples. So let's look at log base 2 of 32. What are we asking?
16.
We are asking, what is the exponent I have to raise 2 to get 32? It takes a product and it spits out an exponent.
5.
5. In this case, the answer is 5. Because 2 to the 5 is equal to 32.
Yeah.
When I say log base 2 of 32 is 5, notice, by definition, that means this. I don't know why I put comma there. By definition, this means this. These two are logically equivalent. So this is logically equivalent to me saying, let's see, what was my x, 32, is equal to, what was my a, 2, and what was my y, 5. So it's just another way of saying 2 to the 5 is equal to 32. Log base 2 of 32 is 5. Logarithms take products and spit out exponents. Exponentials take exponents and spit out products.
Okay.
Good? Let's try another one. Let's look at log base 10 of 100.
Just
Just 2.
Just 2. Because 10 to the 2 is 100. Let's look at log base 10 of 1,000. 3. Good? Let's look at log base pi of pi squared.
2. Wait, no. 1/2?
You overthought it.
It's 2, right?
It's just 2. What do I have to raise pi to? What exponent do I have to raise pi to get pi squared? 2. Right? Okay. Let's look at log base square root of 2 of 4.
4?
Yeah.
Square root 2? Wait, no. 2.
No.
Wait.
What square root? It's 4.
What?
Square root of 2 times square root of 2 times square root of 2 times square root of 2 4 times.
Yeah, 2 times 2.
Root
Yeah.
2 times root 2 times root 2
Yeah,
times
that's
root 2. Those and those give me 2. Those 2 give me 2. 2 times 2 is 4. Okay? So a bunch of different logarithms.
Is there any way, do you kind of have to think your way through it every time? Is there like a formula you can use to calculate it?
No, there isn't a formula for calculating a logarithm.
Okay.
It's just the logarithm.
That's
It's like looking for the formula for calculating multiplication. It's already just what it is.
So odds.
So you gotta just get comfortable with logarithms.
Okay.
Okay. I mean, there are numeric ways of approximating logarithms in cases. That is a thing. It's just we never bother learning those methods because we have calculators. But it used to be something that you would do. Okay. So now, properties of logarithms. What is log base a of 1 equal to?
0.
0. Because a to the 0 equals 1.
Makes sense.
What is log base a of a equal to?
1.
1. Because a to the 1 equals a. Here's your base, here's your exponent, here's your product.
Yeah.
Base, exponent, product. A to the power of 1 equals a. A to the power of 0 equals 1.
1.
This is saying the exact same thing as this, using the definition. Your y, your output of your log is your exponent here. The base is what you're raising it to, and the 1 is the product. Okay. What is log base a of a to the x?
X.
X. What exponent do I have to raise a to get a to the x? X. X is the exponent I have to raise a to get a to the x.
Yeah. Okay.
Yeah. And now you're seeing how these are inverses of each other. Because your exponential, if your exponential function f of x is equal to a to the x, and your inverse function of x is equal to log base a of x, what happens when I plug this into this? What is f inverse of f of x equal to?
X.
It's equal to f inverse of, what was our f of x? A to the x. And so we're asking, what is the logarithm base a of a to the x equal to? You already did it. It's x.
Okay.
So, showing you concretely how they are inverses of each other. Right? Okay. What is the log base a of x times y? Now, there's no reason that you should just know how to do this. I'm going to prove that this is in fact the case. But first, I want to give intuition. X times y here is the product. Logarithms take products and spit out exponents. Right? So this is saying the exponent to this product is the exponent of the first term plus the exponent of the second term. This is capturing the same information as this. Now I'm going to prove that this is in fact the case. Okay? So really quick, I'm going to say log base a of x, whatever that is, I'm going to call it m. Just following the convention we used up here, m for the exponent. And I'm going to say that log base a of y, I'm going to call n. Okay? By definition, what does this mean? This means that x is equal to a to the m. And by definition, this means that y is equal to a to the n. That's just using its definition.
Yeah.
Okay, so now I am trying to prove that the log base a of x times y is equal to that plus that. That's what I'm trying to prove. I'm going to try and prove this formula for you, since I think you guys have never seen this stuff before.
Yeah.
Hopefully it helps get you comfortable with logs. Okay, so this is the same thing as log base a of what is x? It's a to the m. Times what is y? It's a to the n. So we're taking the log of that. If we put the parentheses, they go like that. Now, what is a to the m times a to the n?
That's a to the m plus n.
Plus n.
Perfect. This is equal to the log base a of a to the m plus n.
And then a to the n thing is just equal to
Right, what is the exponent I have to raise a to get a to the m plus n?
n plus n.
N plus n.
M plus n. That's just using this exact property right here. Log base a of a to any exponent, just that exponent. Log base a of a to an exponent, just that exponent. But what is m by definition?
Log of
Log.
Log base a of x plus what is n by definition? Log base a of y. And so you see the exponent of this product is the exponent of your first product plus the exponent of your second product. Is the way like I read that in my head. This logs, they're tough to get comfortable with at first.
Okay.
Okay, so there's that proof. Let's do another one. Let's prove that log base a of x to the k is equal to k times log base a of x. So, in other words, I can bring my exponent out in front.
Okay. Like the derivative.
So it's like if I was doing this product, k times, that's just, I made confusion in the language. I don't want to say it. Okay, but let's prove this. Log base a of x to the k. I'm trying to prove that this is equal to k times log base a of x. That's what I'm trying to prove, okay?
Okay.
I am going to let m be log base a of x.
Okay.
Now, by definition, what does that mean? That means that a to the exponent is the product.
so a m is equal to x.
Yeah.
Okay, so now come and plug into this thing. My x is equal to a to the m. So now I have log base a of a to the m, all raised to the power of k. And now what is a to the m to the k? It's a to the m times k. So this is log base a of a to the m times k.
Okay.
Which is equal to, I mean, you tell me. Just the exponent. What do I have to raise a to get a to the m times k? M times k, perfect. I'm going to write the k first. Times m. Good?
Yeah.
And now finally, what was m? M was the log base a of x. And so log base a of x to the k is the same thing as bring the exponent in front of your log, k times log base a of x.
Okay.
In other words, it's basically stating this exact same property. In other words, taking a product and raising it to the power is the same thing as multiplying that product's exponent by the power. Raising a product to a power is the same thing as multiplying its exponent by that power.
Okay.
I don't know if that helps. Okay, our next one that we want to prove. Log base a of x to the minus 1. Log base a of x to the minus 1. I want to prove that this is equal to negative log base a of x.
Okay.
Using our previous one, what does our previous one say? You can bring exponents out in front. Bring the exponent out in front. So that's the same thing as negative 1 times log base a of x.
So
Okay.
you're saying x to the negative 1, you're not saying the inverse of log?
No, no inverse of logs. Because the inverse of a log is an exponential. We already have notation for that.
Okay.
What does this say in English? It says that the exponent of x inverse is the negative of the exponent of x. Or sorry, of x to the minus 1. You got inverse in my head.
Okay. Yeah.
Okay.
Okay? Alright, next one. Log of a quotient. What is the log of x over y equal to? Log base a, sorry. What is log base a of x divided by y equal to?
Equals x minus y.
Now, already, you can guess at what this is. We know that the log of a product is the sum of the logs.
So that's going to be the difference of the log?
So the log of a quotient is going to be the difference of the logs. It's exactly the thinking that was going on here. The quotient of the products is the difference of the exponents.
So x minus y.
So that's what we're going to prove is in fact the case. Now this is the same thing as log base a of, I can write x over y as x times 1 over y. Right?
Yeah.
Now, using this rule, I can break that product up into a sum.
Yeah.
So this is log base a of x plus log base a of 1 over y, which is the same thing as y to the minus 1. Right?
And you can take that. negative 1.
And now we can bring the minus 1 out front. And so this is just equal to log base a of x minus log base a of y.
Okay.
So that's how we get this rule. And then finally, our change of base formula. Sometimes, right, you notice that I kept changing what our base was here. Maybe I'm solving some problem, like log base 10 of 15 or whatever, and I really wish I had a different base. Well, let's say log base 10 of 32. Now that 32 behaves nicer with my base here were a 2. So I may want to change the base. So that's what this does. I've got log base a of x, and let's say that I wish instead it was log base b of x, some different base. You can change the base, you just have to divide by log base b of a. And we're going to prove that this works.
Okay.
So in other words, this is equal to log base 2 of 32 divided by log base 2 of 10. Those give us the same thing, and that's what we're going to prove. Okay, so let's prove it. So once again, I'm going to let m equal my log base a of x, whatever that is. And this is logically equivalent to, just using our definition, what is it? Which one's our exponent?
A to the m equals.
M's our exponent, A is our base, X is our product.
So a to the m.
A to the m.
a to the n equals x. Okay, perfect. Now, let's figure out what log base b of x is then. So then log base b of x is equal to, well, what's x?
X is
A to the n. So this is equal to log base b of a to the n. What can I do with that n?
You can bring it out.
I can bring it out. So this is equal to m times log base b of a, right? What was m?
That was log of a.
X.
Log base a of x times log base b of a. So log base b of x is equal to log base a of x times log base b of a. You will see that? Now I'm going to divide both sides by log base b of a. So divide this by log base b of a, and I get log base b of x over log base b of a is equal to, if I divide this side by log base b of a, then I just cancel out that term top and bottom, and I'm just left with this, right? Log base a of x, which is the formula we were after.
Oh, yeah.
So, if you cannot get comfortable with these formulas, these are useful to have written down. There's a derivation of them, trying to make them quick to your intuition. It's one of those things that, I don't know, it's always a pain the first time you get introduced to it, going like all the way back to when you were first introduced to division as a kid. It's just a pain the first time until you get comfortable with it.
Yeah.
So, there's logarithms. Now, the author does not prove any of this stuff. He does not show any of that stuff. This was all stuff that the author does not cover. He proves some of these properties in special cases. Let me just explain to you what, well, before we do that, let me go a little bit further, and I'll explain to you why the author's done. So now I'm going to introduce a number to you. Another number. It's a number a lot like pi. It's called e. What is e by definition? It is a limit as n approaches infinity of 1 plus 1 over n to the power of n.
Okay.
Have you guys worked with the compound interest formula?
Yeah. Yes.
No.
No?
Yeah. Some.
For what?
For boundary.
What time is that? Is that 2:12?
Yeah.
All right, we have time to do this a little bit. Let's introduce compound interest. We're going to put a pin in this for a second and introduce where this number, most people see it coming from.
Okay.
So, compound interest, the amount you owe me is equal to the principal I let you borrow times 1 plus the interest rate I charge you divided by n, all to t is the number of years times n.
N is your compounding. rate.
Where n is how often we compound the interest.
Yeah.
So let me give you some concrete intuition for this. Let's say I loan you $100 at a 12% interest rate.
Okay.
After 1 year, how much money do you owe me?
What do I do?
You owe me $112, right? Let's say instead of me charging you all the interest at the end of the year, I'm going to charge you 1/12 of the interest after 1 month, and then 1/12 of the interest after the next month, and then 1/12 of the interest after the next month. So I'm going to charge you the interest, 1/12 of it, 12 times throughout the year.
Gotcha.
So after 1 month, so you start with 100, after 1 month, how much money do you owe me?
101.
$101, because I'm charging you 1/12 of the interest after 1/12 of the year. After 2 months, how much money do you owe me?
2.
No, it's 102 and 1 cent. Because now you've got to do, what's 1/12 of the interest? It's 1%, so now it's 1% of that. And it gets an extra penny.
Sneaky.
Sneaky. And if we were to calculate this over the course of the year, then it would be something like $112 and, I don't know, probably like 60 cents. Making up the number here, but it's going to be a little bit more. And then what would happen if I instead charged you 1/365th of the interest every single day?
You'd profit.
Then the number gets a little bit bigger. It's going to be like 112.65 or something.
Okay.
And then what happens if I split the year up into 1 trillion intervals and I charge you 1 trillionth the interest on each of those intervals? It's going to be a little bit bigger. And now what happens if I break it up into infinitely many intervals, charging you one infinitesimal of the interest?
It's going to approach a number.
Well, yeah, we'll approach 112.75-ish, something. Again, making it up. But, so this is how you charge it, where n is just however many intervals you're doing. If you're going to charge it continuously, meaning every instant I charge you one infinitesimal amount of the interest, then the formula now is just p times e to the t.
Yeah.
And so what we're asking is, what is it as we take the limit as n approaches infinity? N here was how many times we were splitting up.
Yeah.
So R was the interest rate I was charging you. N is, I split it up when we were splitting it into 12 pieces, just to do this very concretely. The amount you would have owed me on $100 would have been 1 plus, the interest rate we said was 1/12, right? If I'm doing that once a month, 12 times, for 1 year times 12. So 12 is the n here, counting how many times we're breaking it up. 0.12 was the interest rate. We just made 1/12 so that the division would come out nicely, and we could think in our heads a little bit. And so this is how you would calculate it. So when you go and you get a mortgage, typically they compound it monthly.
Yeah.
So now, what basically would happen, what does this approach, if I want a now to be the limit as n approaches infinity of this thing? Right? As we do it infinitely many times, and it comes out to P-E-T, where E is this thing right here. It's that limit, and you can see how this is embedded in there.
Yeah.
Interesting.
So that is the same way that E is typically introduced to kids. It's this formula. Okay? Just to give you an approximation for what E is, it's roughly this number.
Are there any other ways of deriving it besides using the compound interest formula?
Yes, there's other ways of coming up with E. There's tons of ways you could define E.
Okay.
To give you an example from geometry, what is the definition of pi?
Circumference divided by the diameter.
If you're a sane person, then we define pi to be circumference divided by diameter.
Okay.
But I could have also defined pi to be,
3 point.
no, I could have said it's going to be the area of the circle divided by the radius squared. Because what is the area? It's pi r squared.
Yeah, that's true.
Or I could have defined it as take the surface area of a sphere and divide by 3/4 or 4/3 r squared.
Yeah.
And I could have used any random formula that includes pi in it to give you any random definition of pi. But if you're a sane human being, this is it. And this is one that gives you some information about this thing. So the author does something similar in defining E. Well, we can't do it yet. So one more thing I need to define for you now is natural log. What is a natural log of x? It's just a log base e of x. We do log base e of x so often that we have a special symbol for it, natural log of x. And it's the most useful base that there is in a logarithm. And you will learn to love when you see this and hate when you see log base a of x.
Okay.
When you take calculus 2. You'll fall in love with natural logs. Now, the author's definition. Here's how the author defines natural log of x. He says, natural log of x, by definition, is equal to the integral from 1 to x of 1 over t dt. And that's what he gives us his definition for natural log. And then he says e is a number such that natural log of e spits out 1. And that's how he defines e. This is very stupid, but it's the way that he does it. And so now, author down the road, he's going to want to use the fact that what is the natural log of something like a times b equal to? Well, we know, since natural log is just log base e, we know from our logarithm rules, what is the log of a product? It's the sum of the logs. This is just equal to the natural log of a plus the natural log of b. Right? And we prove that just using logarithms. The author gives a proof that this is the case, but because he has this horrendous definition, his proof has to use taking derivatives of things to try and figure this out.
Yeah.
It's a nightmare. It's very ugly. It's disgusting. I hate this section 7.2. So I came at it a very different way. I talked about logarithms, which he didn't talk about. And now, what is natural log of x? It's just log base e of x, where e is this number. And you can get as good approximation as you want for this number. Plug in 10 for n here, and that would give you really close to what e is.
Okay.
So, very different from the author, very different from the book on this section. Can't stand the way he comes at it. He makes a mess of everything. But it's all logically equivalent. And so we're going to prove that the author's definition follows from the same definition.
Second one.
The same one.
Okay.
But before we do that, let's just get comfortable with logs for a second now, using our log properties. So, let's look at natural log of 3x to the 4 over 2y squared. And let's get used to breaking these things up into a bunch of smaller logs.
Natural log means just log.
And a natural log is just log base e.
Okay.
But what is the log of a quotient?
It's just
The
them
log
subtracted.
of the top minus the log of the bottom.
Yeah, it's just the log of the top minus the log of the bottom.
Yeah.
So I can say that this is the natural log of 3x to the 4 minus the natural log of 2y squared, right?
Yeah.
Now we can break this up a lot more. This is a product of 3 and x to the 4,
Okay.
right? So this is just equal to natural log of the 3 plus natural log of x to the 4 minus natural log, we can break the 2 out, distribute the minus to each one, minus natural log of y squared. Break all the products into just sums.
Yeah.
With me so far?
Yeah.
And now we can also pull our exponents out. And so this is actually equal to natural log of 3 plus 4 natural log of x minus natural log of 2 minus 2 natural log of y. You see all that? And so you can really break these things down. So now let's do this one. What is this equal to?
Wait, that's your answer?
Wait, that's it?
That's it.
You can't combine that terms?
No.
Why?
You can't go.
Oh.
The point was just to decompose that logarithm into small bite-sized pieces. And so you make these a bunch of individual small bite-sized pieces. For example, looking at head sum, imagine you were asked to calculate the derivative of this thing. Looking at that looks like a nightmare. But then each of these component things
Look easy.
looks really easy. That's just a constant. You'll figure out that the derivative of natural log of x is just 1 over x. That's just a constant, so it goes to 0. And natural log of y is just 1 over y.
What? Weird.
You'll get there, but the point is, it makes the pieces bite-sized in a sense, easy to work with. Whereas you would not have wanted to deal with that thing directly.
You just pull it down, subtract it, and then pull down the exponent.
Yeah, and just use the fact that quotients are taking differences of logs, and products are taking sum of logs.
So we'll just need all those rules.
So let's do this one.
Same thing, you said.
So tell me what the reg.
X squared plus 1 minus the natural log of square root of x, which would be x to the 1/2.
And then take out your.
This one we can't break down anymore.
Yeah.
One of the ways you're going to screw up is you're going to think that a log of a sum is a product of logs. You're probably going to make that mistake.
Why can't you pull the 2?
You can't, because it's not the whole thing raised to a power.
Yeah.
So there's no way to break this one down more.
What's the difference between that one and that one up there?
Let me finish this one really quick. Minus 1/2, we can pull that out, natural log of x.
Yeah.
So up here, x was raised to the 4.
Yeah.
The whole thing was. If this was x plus 1 squared like that, then I can pull the 2 out. But the whole thing's not squared. So it remains just x squared plus 1. It's kind of like if I had a square root, if I have just an x squared there, I can pull the x out. If I have an x squared plus 1, I can't just pull the x out and leave the 1 behind.
I like that. Yeah, that makes sense.
Okay, so there we go. That's how we broke it down. Let's try a really convoluted one now. This one.
What? This is a what?
The natural log of this whole thing.
Okay.
Try and tell me what it is all in one go.
It's 5x
5 times the natural log of x
of 2
plus 2
sine of
natural log of sine.
natural log of sine parentheses pi times x, and then minus by 3
This is a cubed root, so that's going to be a
3
1/3.
halves?
1/3.
1/3.
Yeah, cubed root means 1/3.
Oh, yeah.
Square root means 1/2. Cubed root means 1/3. So minus 1/3 the natural log of.
No, not 2x. So just x squared plus 2.
And there we go.
That's it.
That's it.
That worked.
Does that really make it that much similar?
Yes.
Yeah.
Again, think about trying to calculate the derivative of this thing using some sort of chain rule. You still have to calculate the derivative of the inside.
Gross.
Yeah, that's a nightmare. But once I break it up like this, now calculating the derivative,
It's pretty
lot easier.
straightforward.
very simple. And so that will be one of the applications is you'll be asked to calculate derivatives of horrendous looking things. And the way that you'll do that is you'll stick it in a log, break it up, calculate the derivative that way, and then undo the log, so to speak.
Really?
Yes,
Oh.
That's cool.
it is fantastic. Saves much headache. Okay. So we did all those. Okay, so the big proof now of this section. What is the derivative of a log equal to? So our theorem here is that the derivative with respect to x of the log base a of x is equal to, we're right here, is equal to 1 over x times the log base a of e, where e is this number.
Oh, okay.
With me?
You mean the 2.7?
No, where e is this number. This is just an approximation.
So what's the point of that?
This is its exact definition, and this is what we're going to have to use.
Okay. So, what is
Or something logically equivalent. But let's just get started. So let's see. What is the derivative with respect to x of the log base a of x equal to? Difference quotient. That is going to be the log base, or the limit, sorry. The limit as h approaches 0 of log base a of x plus h minus log base a of x all over h. You with me? Just a definition of a derivative.
Yeah.
Yeah.
Okay, I'm going to pull that h out in front here as a multiplying it by 1 over h. So this is equal to the limit as h approaches 0 of, I'm going to take that and put it as 1 over h times this whole thing. What is the log of this minus the log of that? A difference in the logs is the same thing as, the quotient. So that is the same thing as just the log base a of the quotient of x plus h over x. You with me? Now I'm going to break this into two fractions. I'm going to do x over x plus h over x. So this is equal to the limit as h approaches 0 of log base a of 1 plus h over x. Good? Now I'm going to take, I lost my 1 over h. The limit as h approaches 0 of 1 over h times that whole thing, right? Now I can take that 1 over h and stick it as an exponent inside my log. You can take exponents and pull them out front. That also means you can take whatever's out front and stick it as an exponent inside.
Inverse.
So this is equal to the limit as h approaches 0 of the log base a of 1 plus h over x
to the negative.
all to the 1 over h. Not the negative h, 1 over h. Whatever that coefficient was, just stick it up there.
Oh, okay.
Okay, now I'm going to make a substitution. I'm going to let n equal h over I want n to equal x over h. That's a substitution I'm going to make.
Okay.
You with me?
Yeah.
So now first off, let's notice something. The limit then, as h approaches 0, is the same thing as the limit as n approaches what? As h gets closer and closer to 0, what does n get closer and closer to? Infinity. You see that?
As h approaches 0.
As h gets closer and closer to 0, n gets closer and closer to infinity.
Yeah.
What is the x here?
Just
The x is just whatever we're plugging into a log. I didn't stress this like I should have, but logs can only take positive numbers.
why?
Why?
Because when I raise something to an exponent, I can never get 0 or a negative number. Let me stress this a little bit. Let's look at log base 2 of 0. Before we do that, let's first see let's see negatives. Should have done this. Sorry. Let's look at log base 2 of 1/8. What do I have to raise 2 to the power of to get 1/8?
3.
3 gives me 8.
Negative
1/3.
Yeah, 1/3.
Negative 3. What is 2 to the negative 3? That's the same thing as 1 over 2 to the 3. That is 1/8.
Okay, that's perfectly valid, isn't it?
No, that's perfectly valid.
Okay.
So far we're good. So when I put a fraction here, we get a negative number here.
Yeah.
If I put a really small fraction here, if I put something like 1 over 1024, then the answer would be negative 10. 2 to negative 10 gives me a really small number. And as I put smaller and smaller numbers in here, the exponent gets closer and closer to negative infinity. Right?
Yeah.
Now question. What is log base 2 of 0 equal to?
You can't get anything.
What do I have to raise 2 to the power of to get all the way to 0?
One.
If I raise it to the power of negative 1, 0, 0, 0, 0, 0, 0, 0, that gets me a really small fraction, but it doesn't quite get me to 0.
So it's a negative.
Yeah, as this approaches as logarithm,
As the base,
as the base approaches negative infinity, as my exponent approaches negative infinity, then our product is getting closer and closer to 0.
that sounds.
So once I put 0 here, there is no exponent I can raise 2 to get 0. And there's nothing special about 2. That could have been 10, that could have been whatever. So my x here, whatever the x is I'm plugging in my logarithm, can't be 0 and it can't be negative. It has to be some positive number. All that to say
Interesting.
that x is some positive number divided by a really, 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 really small number, it always turns into a really, really, really big number.
Yeah.
Sorry, we should have had that conversation before I jumped into this proof. Okay, so back, I'm saying let's let n equal x over h. You with me?
Yeah.
So then, flip the reciprocal on both sides. That means 1 over n is equal to h over x. You see that? If this is the case, then this is the case.
Yeah.
Similarly, notice if I divide both sides by x here,
Okay.
then that gives me that n over x is equal to 1 over h.
Yeah.
I'm going to be making two substitutions here. I'm going to be replacing my h over x. That's the same as 1 over n. I'm going to replace my 1 over h. Turns out that's going to be n over x. So I'm just getting ready to make these two substitutions.
Oh.
You with me?
Yeah.
So using all those substitutions, this is equal to the limit now, since we're using n, It's as n approaches infinity. Sorry, my h's and my n's are not very clearly distinguishable. That's the limit as n approaches infinity of log base a of, doing our substitutions, this is going to be 1 plus h over x now is the same thing as 1 over n. All to the power of n over x. And I'm going to write that as n times 1 over x. You with me?
Then you take the 1 over x out.
Perfect. Going to pull the 1 over x out front. So this is equal to the limit as n approaches infinity of 1 over x times log base a of 1 plus 1 over n all to the n.
1 over x times log of a of e.
And the limit of a product is just the product of the limits. So what is the limit of 1 over x as n approaches infinity?
1 over x.
1 over x.
It's just 1 over x. And what is the limit as n approaches infinity of log base a of this thing? Well, the limit of a function, the limit of the composition, you can always just bring it inside the function.
And just put infinity on.
So what is the limit as n approaches infinity of 1 plus 1 over n to the n?
E1. E.
It's just e.
Oh, so 2 or 7, whatever.
Yeah, whatever, but it's just e. There we go. So the derivative of the log base a of x is just 1 over x times the log base e of e.
Baby.
Yeah. So now question. What is the derivative with respect to x of the natural log of u equal to?
1 over u.
It's just 1 over u
log of a
times the log base e of e, because we're talking about natural log, is log base e. So times the natural log of e, and then chain rule, times the derivative of u with respect to x, whatever that is. Just carrying out the chain rule. You with me? Now, what is the natural log of e? What is log base e of e equal to?
1.
Just 1. What exponent do I have to raise e to get e? 1. So natural log of e is just 1. So the answer is just 1 over u times du dx. So in the special case where a is e, notice that this term just reduces to 1. Right?
Yeah.
So that's why that cancels out when we're doing it with u's. And this is why we love log base e more than anything. Because this term always goes away. Because you get a similar term when you take an integral. When you take an integral, you'd have to divide by this term. When you take a derivative, you have to multiply by it. When you take an integral, you have to divide by it. When our a and e happen to be the same number, then it goes away. That's why we like natural log base e. It stops those terms from showing up when we take our derivatives and our integrals. You with me?
Yeah.
Okay, so there we go. We've proved that the derivative of the natural log of u is just 1 over u times chain rule. Really quick, make sure we're understanding this. What is the derivative with respect to x of 1 over, or of natural log of x?
It is 1 over x.
It's just 1 over x.
Okay.
Good?
X is arbitrary.
It's just like everything else. When I said, what was the derivative of x squared? You said 2x. What's the derivative of natural log of x? 1 over x. It's just what it is. You with me?
Yeah.
So let's do some concrete cases. What is the derivative with respect to x of the natural log of 2x equal to?
1 over 2x.
1 over 2x.
1 over 2x.
E. No, not E. What?
Two.
Du
Minus
dx.
times the derivative of the inside. Chain rule.
Oh.
It's the same way that if I would have said, what is the derivative of
2.
something like x cubed plus 1 squared? What's the derivative of this thing? Bring the 2 down. That would be 2 times x cubed plus 1 times the derivative of the inside
3x.
times 3x squared. Same thing here. Times the derivative of the inside times 2.
Okay.
And notice that. Just comes out to 1 over x again. How fun.
Whoa.
Okay, let's try another one. What is the derivative with respect to x of, where was I? This thing, of the natural log of x squared plus 3.
1 over x squared plus 3 to 2.
2x.
2x.
Times 2x. So it's just 2x on the top over x squared plus 3.
Oh,
Look
yeah.
how easy it is to calculate derivatives of logarithms
When it's a natural log.
when it's a natural log. And that's why these rules for taking these complex, now calculating the derivative of something like this, that is not that difficult. You break it up into its pieces like we did before, and then calculate the derivative of each of those bite-sized pieces. And so it turns out to be shockingly easy.
So
Calculating the derivative of the natural log of this thing is way easier than calculating the derivative of it without the natural log.
Yeah.
yeah, it's just getting used to those logs.
So we love these logarithms when we have to calculate derivatives. They are wonderful.
Yeah.
So easy, right?
Well, that's not a problem. The problem is getting it in format.
Okay. So now with that, finally prove the author's definition of natural log.
Okay.
So let's just calculate this really quick now. What is the integral from 1 to x of 1 over t dt?
What is the one?
We need to find something whose derivative is 1 over t.
Okay.
What's the antiderivative of 1 over t? What is the antiderivative of 1 over x?
Is
What's the function whose derivative gives me this?
It's
x. Wait, that's x
Natural log.
plus
Natural logarithm.
It's natural log of x.
Oh,
The derivative of this gives me this.
yeah.
This is an antiderivative of this thing.
That makes sense, I guess.
so you just pull log out.
Have we never ran across that before?
Yeah, we did not know how to calculate this. Here's the way you wanted to do it. Let me take you through the way you wanted to do it and why you got in trouble. Let's look at the integral of x to the negative 1 dx. Same thing, right?
Yeah.
Okay, we're going to add 1 to the exponent,
You get 0.
which gives us 0, and then divide by 0.
Oh.
So we get 1 over 0,
Yeah.
which doesn't work.
Yeah, that doesn't work.
So this was a special case where our chain rule didn't work. And we mentioned that when we came across it, but it's hard to
Yeah.
care when you don't really use it. So now we know how to deal with those, and those come out their own special thing.
Heck yeah.
Sweet.
So, what is the antiderivative of 1 over x?
That's the natural log. isn't it?
Natural log of x. So, to calculate the antiderivative of this, it is going to be natural log of t evaluated from 1 to x.
And you don't change those. Okay.
Well, we plug in the x and subtract what we get when we plug in 1.
Yeah.
Right? So this is just equal to natural log of x minus natural log of 1. What is the natural log of 1?
Natural log of 1 is 0.
0. Any base raised to 0 gives you 1. What do I have to raise e to the power of to get 1? 0. So this is equal to just natural log of x. Okay, so we proved the author's definition. He starts with that as his definition and tries to prove all this stuff weird and backwards using derivatives to do it as he goes.
Why does he do that?
Because this is a really easy starting point moving forward. Let's skip all that work and jump here and move forward. It's just it's not very useful. It's not giving you a lot of insight as to what that e thing is, or even that the natural logarithm is a special case of a logarithm.
Yeah.
So he doesn't even bother trying to make this connection between logarithms and exponentials, and then the fact that the natural log is just a special kind of log. It's a terrible section. I can't believe it. Okay, with that, let's do a couple more proofs.
Proofs or examples?
One more proof. Question mark?
No, we gotta do our trig functions. There's still some trig functions that you don't know how to calculate the integral of. And we've gotta do those ones. So, let's, we're good. We'll calculate this really quick just to give you a feel for it. And then we'll go from there. So let's calculate the integral from minus pi halves to pi halves of cosine of theta.
There's a 4.
4 cosine theta, thank you. Over 3 plus 2 sine of theta d theta. So prior to today, this wasn't one that you would know how to do. But now,
Natural log.
well, it's going to give us a logarithm somehow. But we're going to have to start with the u substitution. What do we want our u to be?
Bottom.
The bottom.
Yeah.
Good chance, since we know how to integrate things that look like this. 1 over x dx.
Oh, okay.
I want that to look like 1 over x dx. So if I do u is equal to 3 plus 2 sine of theta, then it gives me that du is equal to what?
Du is equal to
2 cosine.
yeah.
2 cosine of theta.
Du.
D theta.
T theta. Okay. All right, so notice that we have a 4 cosine of theta d theta. We need a 2 cosine of theta to be the du. Right? So I'm going to use a 2 here and pull another 2 out. So this is the same thing as 2 times the integral.
Oh yeah, that's awesome.
We'll have to change our bounds of du over u.
Yep, which is just 1
Now,
over u du.
let's quickly change our bounds. So when theta was minus pi halves, what was u? So what's the sign of negative pi halves at the bottom of the circle?
-1.
Negative 1. Negative 1 times 2 is negative 2. 3 plus negative 2 is
1.
1. All right, now let's plug in pi halves. What's the sign of pi halves?
0.
1 times 2 is 2, plus 3 is
5.
5. And so there we go. Now this integral couldn't get any simpler. That's just equal to 2 times the natural log of our endpoint minus the natural log of our start point. Oh. And what is the natural log of 1? 0.
Why are
E to what exponent is 1? 0. So we got 2 times the natural log of 5.
Why are you allowed to just
Sweet.
don't you have to substitute them back in?
No, because I changed my bounds. If I didn't change my bounds, I would have had to substitute back in.
Okay.
So you have to do one of two things, either change your bounds or substitute and replace your u's back with thetas.
It's kind of pain.
Yeah.
It's equal algebra either way.
It's true. I guess.
It just would have been more writing to write it again.
And how can you just take du over u and just make that
Look,
natural?
4 is right here.
Yeah.
I take 2 of it and put it there and leaving 2, right?
Yeah.
What is 2 cosine of theta d theta?
It's
What is
du.
2 cosine of theta d theta?
Du.
du. That's exactly what this is.
Yeah.
What is 3 plus 2 sine of theta?
U.
u.
du over u is
2
equal to 1
du over u.
2 du. Yeah, how did you just put that into natural logarithm of 5?
du.
Okay, sorry. One step at a time. So our 2 is here. There's still our 2.
Yeah, I
Times.
get that.
What is the integral? What is the antiderivative of 1 over u? The integral of 1 over x dx is just a natural log of x. The integral of 1 over u du,
Yeah, but x isn't 5.
let me write it this way. This is the same thing as 1 over u du.
Oh, and then you take it from there. Okay.
Okay, So that is equal to 2 times the integral of 1 over u is natural log of u,
Yeah.
evaluated from 1 to 5, which is equal to 2 times the natural log of 5 minus 2 times the natural log of 1. Natural log of 1 is 0.
0. Okay.
Good?
Yep.
All right. So there's an example doing that.
So this is like really useful.
Yes.
Yeah. So now let's calculate the. I probably don't need that. No. So now let's prove. Now we can calculate the integral of some stuff that we couldn't calculate the integrals of before. So we're going to do the integral of the tangent of theta. So tangent of theta prior to today, we couldn't figure it out. Now I'm going to prove to you that this is the same thing as the natural log of the absolute value of secant of theta plus c. So that's what I'm going to prove.
Don't we know the derivative of tangent?
No, you knew how to take the derivative of tangent. You did not know how to take its integral.
Really? Or did
Because here's its integral, and you haven't come across logarithms yet.
it?
Okay, so let's calculate this. So this is the integral of tangent of theta is the same thing as sine of theta over cosine of theta.
Yeah.
I'm going to do a u substitution. What should I let my u be?
Bottom.
The bottom. So u is equal to cosine of theta. And what is du equal to?
Just the derivative of that.
What's the derivative of cosine?
It's negative sign.
Negative sine.
Negative sine theta.
Negative sine of theta d theta. Woo! I have to throw my chalk at you. Okay. So now doing that substitution, this then is just equal to the integral of
U.
negative du
Or U.
over u.
Which is just 1 over U.
Well, remember we have the negative there. So this is the same thing as negative 1 times the integral
Yeah, there we go.
of 1 over u du. Trying to write it how you might like it.
Yeah, I like that.
Okay, you like that. Okay, so this is equal to now negative 1 times the natural log of the absolute value of u plus some constant. You with me?
Yeah.
Which that is equal to the natural log of the absolute value of what was u? Cosine of theta.
Plus some constant.
And I'm going to put this minus 1 as an exponent. So I'm going to take that and raise it to the negative 1. And then plus our constant.
Why are you allowed to do that?
Log base a of x to the k is k times log base a of x.
Okay.
You can bring your exponents out of your logarithm. And you can also shove them back in. So I can take that negative 1 and view it as u to the negative 1.
Okay.
So that's what I'm doing. My u is cosine theta to the negative 1. What is cosine theta to the negative 1? What's the reciprocal of cosine? Or in other words, what is 1 over cosine of theta?
Sine over 1?
What is 1 over cosine of theta?
It's
Cosecant.
or
Is it secant?
secant.
It's most likely the one I said we're going to prove it's going to be.
Oh.
Just playing the odds there. So this is equal to now the natural log of the absolute value of secant of theta plus c. And why the absolute value there?
Because
Can't be negative.
Yeah, logs can't be negative. I can't take some base, raise it to an exponent, and get a negative number out of that.
Okay.
A positive base. Another thing that we didn't talk about is that logarithms, the a there is always a positive number. Why is it always positive?
Yeah.
Think about something like this. Negative 2. First off, to the 1/2. You already see the problem that you get there,
Yeah. Yeah.
because now you're talking about the square root of a negative number. So your base is always positive with the logarithm. Okay, anyway, so there's a proof for that one. Now, the proof for cotangent is almost identical.
It makes sense. Yeah.
Yeah.
So, we'll, well, I guess we could do it if you want. Let's do the proof that the integral of cotangent of theta, d theta, is equal to the natural log of the absolute value
Cosecant.
of cosecant of theta plus c. Can't remember if there's a negative sign there. We'll figure it out what it is. I don't have these formulas memorized. So it's going to be something like that.
Yeah, we get the idea though.
So let's really quick evaluate this. This is the integral of cosine of theta d theta over sine of theta, right?
And just u sub.
Now look at this is we already have in the top the derivative of the bottom. What is the derivative of sine of theta? Cosine of theta d theta.
Yeah.
Right? And so this is already du over u. So I'm just going to go straight to that's obviously just the natural log of the absolute value of sine of theta.
Okay.
Now, I think that their formula, they have a cosecant there.
And they're what?
I think the formula, should have pulled it out. You have your book, don't you?
Yeah.
See if you can find it in your book really quick. In section 7.2, the antiderivative formulas.
Oh, for the actual.
I'm wondering if they have a negative,
In front of the sine? Or the cosecant?
Where do they cosecant?
yeah.
Yeah, they have negative natural logarithm of cosecant u plus cotangent u plus c.
Okay, that's interesting.
For the integral of cotangent.
Oh, cotangent. That is natural logarithm sine of u plus c.
Oh, so they did sine of theta? Okay. So here's how they left it. I wondered if they were going to put a negative there and make it a cosecant. But they just left it sine of theta, it sounds like.
Okay.
Right?
Yeah.
Okay. For our next one, we're going to do the proof that the integral of, let's see, what's next? Secant, I think? Keep following along in your book, make sure I'm right.
We didn't.
Secant of theta
Yeah.
comes next, right?
Yep.
Okay, let's do this one. And we're going to prove that this is equal to the natural log of the absolute value of secant of theta plus tangent of theta
Which is in that is.
plus c. No, that is not its derivative. The derivative of secant is secant of theta times tangent of theta.
Oh, okay.
So this is quite different.
Okay.
Now this one, you do this one's proof weird. So the integral of 1 over secant of theta is what we're calculating, right?
Yeah.
For reasons unknown to you, but you'll see in a minute, I'm going to multiply this top and bottom by secant of theta plus tangent of theta. And then we still have our d theta here. Okay, very strange why I did that.
Yeah.
Now, how's, why did I put this in the denominator? We're doing the integral of secant theta. I was going to write it as 1 over cosine.
Oh.
Okay, sorry. Everything looks normal now, right?
Yeah.
Integral of this, and so far I just multiplied it by 1. Now, the reason we multiplied it by 1 is partly to motivate it is, well, I know I'm going to be using a natural log, and so I don't have anything in the denominator right now. If I would have viewed that as 1 over cosine of theta, well, I don't have its derivative upstairs to do anything with. So I'm kind of stuck.
Yeah.
So when you're stuck, you have to either come up with a clever way to add 0 or to multiply by 1 to make it workable. And we'll see how multiplying it by this 1 suddenly makes it workable. So now this makes it the integral. In the numerator distributing, I have secant squared of theta plus secant of theta times tangent of theta all over, in the denominator, I have secant of theta plus tangent of theta, d theta. You see all that? Okay, now what is the derivative of secant?
1 over.
The derivative of secant.
It's
Tangent times secant.
Secant times tangent.
Yes.
What is the derivative of tangent?
Same thing.
Secant squared.
Yeah.
Secant squared.
So you see now the derivative of the bottom thing is right here. If I took the derivative of this,
Oh.
right, if I call this u, then this is exactly du.
Oh, so you just use substitute. Okay.
So yeah, you can u substitute it. I can say let u equal secant of theta plus tangent of theta. Then my du is going to be, the derivative of secant is secant times tangent, secant of theta times tangent of theta, plus my derivative of tangent of theta is secant squared of theta, and then d theta multiplied by the whole thing, right? So notice du and u.
Yeah.
This is just equal to the integral of du over u, which is equal to the natural log of the absolute value of u plus c. But what was u? It was that. So this is equal to the natural log of the absolute value of secant of theta plus tangent of theta plus c.
Solve- Oh, okay.
And now, doing the integral of cosecant, you do the exact same thing, except for you multiply it top and bottom by cosecant plus
Instead.
cotangent. And the only difference is when you calculate the du, it comes out negative here. So when you do cosecant, it just is the integral of the cosecant of theta is just going to be negative the natural log of the absolute value of cosecant of theta plus cotangent of theta plus c. But the proof goes identical. Just replace your sines with cosines or replace your secants with cosecants and your tangents with cotangents. And it's identical. The only difference is the algebra here, you'd get a negative, which is what accounts for the negative there. Make sense?
Like it.
Okay. And then our last problem, you're going to have to help me out again. I can't access my book.
Did we just do secant?
Yeah, so we're done with the trig functions. Now it asks us to calculate the derivative of some horrendous thing. So, example 5, read that to me. What does y equal?
Find dy dx if y is equal to x, parenthesis x squared plus 1 close parenthesis x plus 3 to the 1/2 all over x minus 1 if x is greater than 1.
What was the denominator?
X minus
Okay.
1. When x is greater than 1.
Okay. So, x greater than 1, simply making sure we're not dividing by 0 down here. That's all that matters for. Outside of that, we don't care about the domain. Okay. So now I'm going to calculate the derivative of this thing. You with me? And we don't want to do it the hard way.
Question.
I wish that this was in a logarithm. If this was in a natural log, then I could break this up into its pieces and then calculate that way, right?
Yeah.
So here's what I'm going to do. I'm going to say, you know what? The natural log of y is equal to the natural log of x squared plus 1 times x plus 3 to the 1/2 all over x minus 1. Right?
Apparently.
Just take the log of both sides.
Yeah.
Yeah. So now, what does natural log of y equal? Let's break this up into all its pieces now. That is going to be the natural log of x squared plus 1 plus 1/2 times the natural log. Sorry, my chalk is slanted weird. Get very quick. There we go. The natural log of x squared plus 1 plus 1/2 the natural log of x plus 3 minus the natural log of x minus 1. You with me? Just breaking it up into its components. Now let's take the derivative of both sides.
Wait. Okay.
Okay, so taking the derivative of both sides, what's the derivative of the natural log of y?
Which one?
1 over y
dy.
times y prime. The derivative of y with respect to x, whatever it is. Remember, y prime is what we're looking for.
Yeah, but that's the same as dy, isn't
dy dx.
it? Yeah.
Yeah.
And then over here, let's see, what's the derivative of this thing?
2x.
It's over x squared plus 1, and then chain row, we need the 2x on top. Over here, this is plus x plus 3 in the bottom, but a 2 in the bottom. So this is going to be 1 over 2x plus 3, or 2x plus 6. Just multiplying it by 2.
Oh, I see. Okay.
And then minus 1 over x minus 1. Right?
Yeah.
So 1 over y times y prime equals this thing. But I'm looking for what y prime equals. So multiply both sides by y. And finally, I get y prime is equal to y times this whole thing. Right? And what is y? It's just that. So it's equal to y
Yeah, crazy.
times this whole thing.
Is there any simplification?
Nope. We've already got this common stuff all factored out.
Saying it doesn't get any simpler than that.
No, this is already pretty well simplified. We already factored all this out of these three terms.
Okay.
There it is. Look how easy that was.
Yeah.
Started up there, pulled it.
We started right here.
Took the derivative, times it all. Okay.
That would be much easier than figuring out that thing by hand. And even if we were given a problem like this, find the derivative of that, it wouldn't have been much harder.
We just break it up.
Yeah, these natural logs makes like you can break it up into bite-sized pieces very easily. And then calculating the derivatives, super easy.
Yeah.
So there we go. That's the end of that section. I know that was a lot because I covered a lot more than the author does.
What? We covered 7.1, 7.2.
Yeah,
7.1 is way more difficult.
7.1 is just that, it's pretty.
it
Yeah.
is what it is. I don't know what's easier, what's harder. Okay, any questions you want recorded?
I think we're good.
There you go, your second to last lecture. Almost done. Don't trip at the finish line.